Hello and welcome to this presentation. My name is Ladislav Straka and I will talk about universal temperature dependence of twinning stress in nickel manganese gallium 10M martensite. I would like to acknowledge my colleagues and also the Czech Science Foundation which supported this work, and if you would be interested in more details of this presentation, you can also search in related publication, which is highlighted here in yellow. The motivation for this work I would like to illustrate using few animations. First animation showing the ferroelastic martensite, and when you apply the external stress on it, you are able to switch between the martensite variants. The mechanical energy to overcome is equal to twinning stress times distortion of the lattice. But what is more interesting, in magnetic shell memory alloys, you can do similar thing using the magnetic field. We are limited in energy by magnetocrystalline anisotropy, or in other words, the magnetocrystalline anisotropy is the maximum magnetic energy which is available for the effect. And so we have some condition that this magnetic energy should be larger than mechanical energy in order that effect can happen, and from that we have some condition for the twinning stress. So the twinning stress should be less than some value, and practically this value is 3 megapascals. So we can think like that. And if we are able to achieve this condition, only with this condition we can think about some fancy devices which use this magnetic shell memory effect. Like on the left, it's very simple laboratory actuator which is moving some part. In the center we have magnetic shell memory pump, which is a little bit more advanced. And on the right we have some professional device from Eto Magnetics. So twinning stress is the force or energy you need to apply to move the martensite twin boundary. And how to determine this is actually very simple. So we just take the single crystal, we apply stress on it, and we measure the stress strain curve. And as twinning stress, we determine the position of the plateau on this stress strain curve. Now we look on the development of twinning stress with temperature. So here on the x-axis, we have, for some reason, not absolute temperature, but distance from martensite transformation. And on y-axis, we have twinning stress. And this is collection of data from several reports. And what we see that there is actually quite strong disagreement between the reports, because some reports show linear dependence, some show large slope and low slope. So there are significant differences between reports, and typically there is no characterization of twin boundary type, which is relevant, which I will show later, and the crystal quality. So aim of this work was to clarify this situation. And what we did, in contrast to previous works, we really very well characterized our crystals. We took in account the twin boundary type, so we have well characterized twin boundaries. And from my point of view, what is also important, we used few different crystal sources to avoid any bias from some particular production method. And if we consider now the limit which I discussed a minute ago, we can see that this temperature dependence is really very relevant, because it's deciding if the crystal is working under some temperature or not working as magnetic shell memory element. And now I come to our experiment. So we studied materials with nominal composition nickel 50, manganese 28, gallium 22. We had 4 producers. So we have some list of basic parameters of materials here in this table, but I would like to mention the producers. So one was Charles University from Czech Republic, Second was Boise State University from USA, Institute of Physics in Prague, from Czech Republic, and last one was commercially obtained, last crystal, from Goodfellow, Cambridge. This slide I prepared to give you some notion about the size of the crystals. So they were typically 1 to 2 centimeter long and few times few millimeter in cross section. And what we typically do first, we look on the sample using optical microscope, or more precisely, we do some mechanical training and then we look using optical microscope. And this is quite typical figure which we can see here, like traces of twin boundaries, and some traces are straight along exactly 101 crystallographic direction, or on the face is along the 100 edge. But we have, and this is twin boundaries type 1 actually, and twin boundaries type 2, they differ crystallographically, which I will not discuss here, but what is relevant is that these boundaries are tilted 6 plus minus 6 degree from type 1 twin boundaries or from exact 100 crystallographic direction. So traces are tilted 6 degrees away. And here are the examples from each of the 4 producers, what we can see using optical microscope. In Charles University sample, we were able to create type 1 twin boundary and type 2 twin boundary. In BSU, it was the same. In FZU sample, we were able to create only type 1 twin boundary. Unfortunately, we have some small grain there, so which is probably the reason. And in Goodfellow sample, we were not able to create pure type 1 nor pure type 2, only some kind of mixed boundary where we had like some parts, it was consisting of parts of type 1 and type 2. What is important here on the right, you can see the animation, and you see that when we compress or pull the sample, this type 2 twin boundary moving easily while type 1 still staying on the spot. So it's immediately we can see that type 2 twin boundary has lower twinning stress or higher mobility, in other words. So there is no phase transformation here. This is just switching between two martensite variants, which one has c-axis along the stress and the other one has c-axis perpendicular to stress. And here you can see the detail of boundary in Goodfellow sample, and it consists of segments which are, let's say, straight, and then there are segments which are plus and minus 6 degree, like misoriented comparing to these straight segments, and this is interpreted as segments of type 1 twin boundary, which are these straight, and then we have this misoriented plus minus 6 degree, it's type 2 twin boundary. So we were not able to create pure type 1 or type 2. Always it was some kind of mixture, some mixed type 1 plus type 2 twin boundary. And here are the examples how we measured. So you can see we took samples, we compressed repeatedly many times, and we obtained the stress strain curves. And you can see we were always watching the boundaries propagating, so we could distinguish the cases with like many twin boundaries, which sometimes happen, from cases with single twin boundaries, which is more important for us, and because it's giving the clear information about propagation of one boundary. And I would like to emphasize that we really care about these kind of problems, this crack interaction or boundary-boundary interactions. So, and the twinning stress is determined as position of the plateau when there were no problems. And here is summary of these room temperature measurements. We can see that, okay, in crystals where we are able to create type 1 and type 2 twin boundaries, we separately measure both of them, and in the rest of crystals we measure what we have. It means type 1 in FZU sample and this mixed Bondari in Goodfellow sample. And now we compare these measurements with the crystal properties. And one property which is, I would say, critical or very important is the chemical homogeneity of the samples. And what we can see here that on the right there are some maps of chemical composition which we measured using X-ray fluorescence spectroscopy. And some parts are missing because, for example, this BSU sample size is limited. In CU sample, unfortunately, it got broken in some additional experiments, so we could recover only a small part. But anyway, what we see that 3 samples, CU, BSU, and FZU, they show only smooth compositional gradient. It corresponds to the case that we can create type 1 twin boundary, type 2 twin boundary. Yeah? In Goodfellow sample, we can see very sharp changes in composition locally. So there is some kind of dots in the map. These spikes in composition, it means there is some problem in the crystal or some inhomogeneity. Maybe it's some impurity. We cannot say exactly from this map, but definitely the crystal is not chemically homogeneous. And this is probably reflected in this inability to create this pure type 1 or type 2 twin boundary. And we also measured crystal mosaicity, which I would like to introduce here in this small figure, that no crystal is truly perfect. It consists of mosaic blocks which are a little bit misoriented, and you can see this misorientation using X-ray diffraction, for example, in omega scans when you obtain typically several peaks corresponding to these individual mosaic blocks. The measurement is on the right, and what is important here is this vertical direction. Really, the cut along the vertical direction gives the degree of mosaicity. So more broader or more peaks along vertical direction, it means larger mosaicity. And what we can see is that the smallest mosaicity really is in FZU crystal and CU crystal, which are those two on the left, and we have large mosaicity actually in BSU and Goodfellow crystals. Again, Goodfellow crystal is worst properties, and so this can also have effect, or this large mosaicity can have some effect on this inability to create pure type 1 or type 2 twin boundary. But when we look on BSU, the mosaicity is comparable. So mosaicity itself cannot be the main reason for these problems with inability to create type 1, type 2 twin boundary. So far this was all room temperature measurement, but how do we measure at low temperatures, which is interesting for us? One possibility is to measure directly. Simply you cool the crystal and you compress, but this is experimentally not that simple. But it was done by Okamoto. I did this also in some of my previous works. But what is actually more simple, that you install the crystal in magnetic field at some temperature, and then you measure the reorientation of Martensite variance. And when this reorientation happens, we can see it as a very sharp jump on magnetization curve, and this jump occurs on so-called switching field. And from this switching field, we can actually determine the corresponding twinning stress. Okay, we prepared the single twin boundary in sample, we placed to magnetic field, and then we measured the switching field at different temperatures, and what we got is switching field as a function of absolute temperature, which can be recalculated also to distance from the Martensite transformation. And more importantly, from this switching field, what we obtain is twinning stress using this formula. Again, it's plot as function of relative temperature. It means distance from martensite transformation. So what we see is that we really have three characteristic regions, and like type 1 twin boundaries, they show large slope, so large increase of twinning stress with decreasing temperature. Type 2 twin boundaries, they show very small increase of twinning stress with decreasing temperature. And we have that mixed type twin boundary, which is somewhere in between. And what is important here that you see it's like differently produced crystal, different producers, and across all these variables, let's say, the dependencies are, they have some scatter, which is understandable, but in principle they are the same or very similar for type 1 twins. So there's some universal dependence for type 1 twins. They are flat for type 2 twins, and mixed type twins, one would expect actually that the twinning stress is somewhere in between. So this is what I consider major result of this work, showing that the twinning stress dependencies are really universal. And what is last to do is to compare with previous works, and which are shown now on the left, and what we can interpret these previous disagreements using our results now. And yeah, so we have type 1 and type 2 twins. So this is very similar by myself. So this is very similar to what we obtained. So we are in correspondence with previous results. But this is yet another producer. These samples on the previous works, it was from Adaptamat. And yet it still follows the similar or the same universal dependencies. And then we have this Solzhenko, which I think, let's say, it seems that it reasonably fits to this type 1 twins region. So probably he had like type 1 twins. And then we have this Hechko, which is somehow the dependence look like somehow exponential. And but in any case, it's between type 1 and type 2, so I would suggest that this was mixed type twins. And Okamoto, it's also in between. I would say probably also mixed type twins. And additionally, I would like to emphasize here is Okamoto. He measured on stoichiometric alloy, so which maybe have also some influence. So after showing this main result, I would like to summarize and conclude. So we studied 4 differently produced crystals. We can see that sharp chemical inhomogeneities have large effect on twin Bondari character, and smooth chemical inhomogeneities or mosaicity, the effect is smaller or there is no effect. So the main conclusion for me that in imperfect crystals, the control over twin boundary character is difficult, and temperature dependence of twinning stress, it may be ambiguous. But if you are able to create pure type 1 or pure type 2 twin or twin boundaries, then they always show universal temperature dependence of twinning stress. And this is all. I would like to thank you for your attention and for watching till here. And for the end, I would like to share with you one micrograph of martensite needles. Thank you and goodbye.